a long time ago. A long, 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 long time ago. Before there were any humans, before there were any plants, before the animals, a long time ago. Before the earth was born. A long, long, long time ago. Before the sun shone, there was a cloud. A cloud stretching almost beyond our imagination. There was a cloud, a nebula made of helium and hydrogen. And this cloud was asymmetric, lumpy in some spots and so thin in others, though stable, and drifting through the cosmic ocean. Far away from this cloud was a star, our ancestor's star, who lived a whole life and died. And when stars die, they implode and explode. Supernova. This supernova explosion rocked the cloud and infused it with metals that the star had made through their life. Now these waves of gravity shook this cloud, and the lumpy spots got lumpier thanks to gravity. And the hydrogen and helium were coalescing, clumping together closer and closer. In this positive feedback loop, the more they grew together, the more they attracted others. The hydrogen and helium got closer and closer. And through friction, they started to make heat and began to glow. A proto-star, our young sun. Thanks to gravity and angular momentum, a disk formed. Spinning around, our sun was growing and growing. Eventually, the energy built that there was light. The friction turned to fusion, elements combining. And around our young sun, the protoplanets started to form so fortunately. Within the development of solar systems, there's a narrow window where planets are able to form, and we were so lucky. First, in the outer reaches, the gas giants formed, Saturn and Jupiter. They were just far away enough from our young sun that the elements didn't burn up. They were able to come together and coalesce, and because they formed first, they grew largest. As our sun slowly began to stabilize, the rocky planets formed on the inside. Mercury, Venus, Mars, and Earth. Though this was well before their names, well before they were even planets, they were simply forming rocks. With gravity, they grew, spinning around our young sun. There was another protoplanet named Thea, who spun around the Earth as well. They were further and closer and further and closer. Because in one moment, they combined and they merged. They combined and they merged. This huge cataclysm. Planets colliding. Can you imagine? They combined and they merged and they made a third, their daughter, Luna, who to this day spins around her mother. See the stars on her body? She protects us. This time period was no place for life. Heavy bombardment, asteroids colliding on her planet as she's growing and growing. With Moon, the daughter, it complexified our gravitational field and it helped to protect our planet. Now Thea, the other mother of the Moon, she did not just bring that cataclysm. She brought gifts. She brought gifts. She brought the gift of her body, iron. So deep within our Earth, there is iron. So much iron. This iron in the center is spinning molten. This molten iron creates a magnetic field that protects our planets from the cosmic rays, the cosmic winds, which would blow all life off our planet. All would not be possible. Iron at our center, spinning a magnetic field. That cataclysm, that collision, it tilted our Earth. We have seasons now, 23 degrees. It slowed our planet down to our circadian rhythm, 24 hours. Though too, Thea brought another gift. The gift of water. So much water. So suddenly our planet, rich in water with the Moon, our daughter, who's pulling on them, water creating tides, dynamism, our Earth is complexifying and changing over time. And two, look at our Moon, she was closer, so much closer, and we're losing our Earth. She's losing our Moon. One day we'll release her out on her own, just like all of our daughters. She'll go. But don't worry, it's really slow. She's losing our Moon at the speed that our fingernails grow. So you can watch too if you want. Every time you clip your fingernails, you can now, oh, the Moon. A little further away now. We can look at her with some longing. It's up to you. So Terra, our Earth, with a daughter, the Moon, rich in water, with a magnetic field that tilts with seasons, tides. Well, things are changing. This heavy bombardment period ends. All that rock and fire coming from the sky slowly dissipates as our solar system develops and stabilizes, and our Earth is an ocean. Hot ocean, still cooling every night. Hot ocean. zone, not too close to the sun, too hot, but not too far away, too cold. And with an internal energy, that molten iron, there's a source inside as well. Salinity, acidity, the temperature and pressure, carbon and hydrogen and nitrogen and phosphorus and oxygen and sulfur. These are the primo ingredients of life. Primo ingredients of life. All the while, all these elements are mixing and matching, interacting and changing each other. And molecular complexity increases. These repeating patterns emerge. Because when something works, it happens again. When something works, it happens again. RNA appears. The first little bits of life, though perhaps as well comets from the stars infused with spores, archaea, lichen, protozoa, bacterium. Perhaps life came from afar. Likely, homegrown life appeared on our planet, deep in the ocean vents, the thermal pools and hot springs, where there's energy and salt. Energy. So 3,800 million years ago, Luca lived and died. Our last universal ancestor. Our last universal common ancestor, Luca, our grandmother. The grandmother of all of life as we know it, except perhaps for those that came from way far, which are coming all the time too. I don't know if you noticed that. But there's little ice comets, tiny microscopic comets, see, they're here right now, that are raining into our atmosphere from afar, perhaps fused with life. Luca, the prokaryotes, single-celled organisms, their internal bodies were like soups. They had a membrane and a metabolism. Self-making, they repair, they heal. That's one of the tenets of life. Autopoiesis. Autopoiesis. This is the agreed upon definition. The agreed upon definition of life. Here we go. Autopoiesis, self-making. We have a membrane that's porous. We choose what to take in and what to let out. Our metabolism. This choosing. Can I eat that? Hundreds of millions of years pass by. The prokaryotes, stromatolites, they change. They change and are changing their environments so slowly. That's what life
to our Goldilocks size, that our planet is just the right size, just the right density, that continents begin to form, that land pushes up out of the sea. The continents, they move slowly, so slowly, the tectonic plates shifting. And all the while, life is changing and trying and dying and living and dying and living and dying whole lives, hundreds of millions of years, whole lives. And life inherently, innately is creative, changing and being changed by our environment. Slowly, the bacteria, they start to learn something new, a new trick. Oxygenic photosynthesis. Oxygenic photosynthesis. Our atmosphere at this time was mostly carbon. Breathe in the carbon, combining it with water, splitting it with sunlight, and releasing energy 10 times. The energy is now available for all of life. And there's this byproduct, their waste, oxygen. Oxygen at this time was very scarce, but it didn't build quite yet. In the seas, it combined with iron and zinc. Iron and zinc. Iron and zinc. 100 million years go by. 100 million years. When bacteria learn something new, they don't just keep it to themselves. They don't just teach their kin. They share it with each other. Horizontal gene transfer just takes one. Horizontal gene transfer. It only takes one bacteria to learn something new. And if it works, they repeat. And they share that knowledge with each other in the form of genetic information. Can you imagine if we could do that? I think we can. I think we do. So, this trick, oxygenic photosynthesis, it's spreading throughout the seas. And oxygen is forming and warming our planet. And cooling and warming and cooling and warming. So as these photosynthesizers, as they're growing and living and dying, they're sequestering carbon out of the atmosphere, which cools our planet down. We all know that carbon is a greenhouse gas. It's like an insulator on our planet. The heat that comes from the sun reflects off the surface, but then gets trapped by the carbon in the air. So with photosynthesis, that carbon is being sequestered, is being held and brought into their bodies, turned into glucose, C6H12O6, sugars. So what happens? Our planet is cooling because of these photosynthesizers, and these other bacteria are starting to lick their bacterial lips. Can I eat that? They ask. Oh yeah. They do. And so what we start to see are these feedback loops that are photosynthesizing bacteria who are sequestering carbon out of the atmosphere and cooling our planet down. And then the ones that eat them really ferment their dead bodies to get that energy that they made from the sunlight and the water and the carbon. They ferment them, they eat their bodies, releasing that carbon back into the atmosphere in the form of carbon dioxide and methane, warming our planet. So this cooling and warming and cooling and warming thanks to life. Suddenly, life starts to have a planetary effect. Life starts to change our planet's atmosphere. Life starts to regulate the composition of our planet. Gaia. Comes to life. Some 2,800 million years ago, Gaia. Life starts to change the conditions on our planet, making our planet livable for more life. The continents mature, shallow seas, stromatolites as colonies of bacterium, growing huge stone-like structures. Huge stone-like structures. Glaciers, ice, huge ice. That trick, the photosynthesis, it spreads far and wide in our planet. The atmospheric composition changes, the great oxidation. At this point, there's 1% oxygen in our atmosphere. Though thanks to these other effects, our planet gets cold. Colder and colder, the ice grows from the poles, reaching up towards the equators. Our planet is like Hoth, a snowball Earth. Oh, so cold. Life likely survived deep in the oceans near the vents, just subsisting and waiting and changing and changing. What saved us this time because it was close. What saved us this time because it was close was the nitrogen getting released thanks to life combining with oxygen, nitrous oxide. Our planet laughed herself back to life. Gaia! All this oxygen, it's affecting our planet and growing. And as oxygen lifts up higher and higher, it changes as well. And suddenly, we have an ozone layer, O3, which protects our planet from the cosmic rays of the sun, really the UV. We see what UV does to our skin and our clothes. It makes it very difficult to build DNA and become more complex. At this point, life wasn't able to fully be in the photic zone at the surface of the sea because of the UV. When they were trying new things, they would die, get broken apart. So the ozone layer allowed life to reach up into the surface waters. much oxygen, and there's no waste. There's no waste. So some of them, they learned something new. They learned a new trick. Respiration, breathing. New nutrient cycle appears. Gaia. Oxygenic photosynthesis. Carbon out of the atmosphere. Combined with water. Split with sunlight. Cools our planet down. Making those tasty sugars. And remember what they ask always? Can I eat that? Yes. Oh yeah. Respiration. Combining oxygen with the sugar, splitting the hydrogen bonds, releasing energy and carbon that warms our planet. Every breath we take, it warms our planet. Every breath the plants take, that cools our planet. This ancient relationship, warming and cooling. This is Gaia. Respiration opens up even more energy. It doubles the available energy for life. Years pass by again. Endosymbiosis. Endosymbiosis. Because once, likely many times, one tried to eat another. They maybe said, whoa, let's make a deal. Don't digest me. I'll live inside your energy for you. You provide a body. Cells learn to work together. Perhaps it was one trying to eat another. Perhaps one was broken. And a little one came inside them, found solace and home, and helped them to heal. Endosymbiosis. This gave rise to the eukaryotes of which we are a part. The simple cells, prokaryotes from before, whose insides were simply metabolic chemical soups. Suddenly organelles started to form. The mitochondria, who are inside each one of our cells, they once lived free. We see in their DNA that once they lived free. But now we work together. Hundreds of millions of years pass by. Life is changing and changing and being changed and changing their environment. Hundreds of millions of years pass by. Life is changing and learning and growing and trying new things and failing and living and dying and trying and failing and trying and failing. So many lives, so many tries. Though another succeeded, the chloroplasts this point, life was in the seas, the land was rocky. It's likely that in some freshwater ponds there was life building and bubbling and growing and trying and dying and living and dying and changing and being changed. Now our planet is still rich in water, and if it was just up to physics and chemistry and cosmology, we would have lost our water by this point. It's likely that on Venus and Mars, the other rocky planets, maybe even Mercury for a moment, it's likely on Venus and Mars there was water, there were oceans. But they weren't lucky. They weren't as lucky as us. They didn't have life. They didn't have that internal magnetic field that helped to keep the water here. They didn't have life like us. Had it not been for all of the life on our planet, at this point we would have lost our water too. Our planet would have died and perished, desiccated. The life is changing the environment and the rocks, the hydrology, the meteorology, and creating stable conditions for life to express. So slowly on the rocky surface, where there's no life, maybe just in the ponds, but the continents were barren, just rock. They were slowly, so slowly, life starts to creep up onto the shores, again through collaboration. The proto-lichens, which is a collaboration of yeast, fungi, and algae. The lichens, they creep onto land, and they mine rock, and they photosynthesize from the sun, making sugars. They're like full communities. And two, did you know, they're basically immortal. They don't die of old age. We see them on gravestone. They'll be there. They've been here the whole time there's been life on land. And they live and they die. They're so thin, but as they die, their bodies decompose. Soil. Making a way for plants to slowly creep onto shore with the help of the fungi, the labyrinth beings. Now these lichens and plants, they are mining the rock with their roots. They're cracking the rocks open to mine the minerals, using water to swell and crack. And when it rains, the water combines with carbon, making carbonic acid, the bubbles and fizzy drinks that bubble, those bubbles we love to drink. Those bubbles, they unlock parts of the rock, calcium and silica, sequestering carbon, sending those minerals out to the sea, where algae turn into their bodies. And our planet cools, it gets colder and colder. Another snow on Earth. It gets so cold, the glaciers glaciers creep up to the center, to the equators. Life subsists somehow. Hundreds of millions of years of ice and life subsists somehow. As the glaciers recede, the Cambrian explosion, calcium in the seas thanks to the lichens, shells, and bones, spines, and eyes. Animals can see suddenly, and our planet looks different. And when we see, we touch. So life is affecting our planet even more. And diversity and explosion, the Cambrian explosion, diversity of life, spines and shells and eyes. 600 million years ago. Plants on land, great coral reefs in the shallow seas, amphibians creep onto shore, insects begin to fly, reptiles with scales and feathers. And the plants, well, all of them are trying new things. Again, they're trying and failing and trying and failing. And some of the plants, they learned something new. It was a breakthrough in technology. Lignin, wood, these large, complex carbon chains allowed the plants to reach up. They make wood look around. We're surrounded by it. Surrounded by this lignin, this wood. But this was so ahead of its time. No one knew what to do with all this wood. So the first forests are growing taller and taller, and they're living and they're dying, and they're living and they're dying, and they're living and they're dying, and the wood is building. No one knows how to break it down. There's no nutrient cycle for that carbon. So our planet gets colder, the carbon sequestered in the wood. For 60 million years, this wood is building and building and building. And our planet is cooling and cooling and cooling and cooling. Ice. It was close. So close. Again, we almost didn't make it through. Earth was about to appear, and it could have wiped all of life out. Though fortunately, as always, life is trying and failing and trying and failing and trying something new. This time the fungi, they learned how to break down releasing that carbon back into the atmosphere, warming our planet. It's close. The continents are forming still, moving across the oceans as they do. At this point, the continents are getting closer together, and Pangea forms a supercontinent. And as they form, it sets off a chain reaction of volcanoes, super volcanoes, and our planet gets warmer and warmer and hot. so hot. Our planet warms to 8 degrees Celsius above where we are now. We call this period the Great Dying. We lost so much life. Truly tragic. 96% of life in the ocean vanished. 70% of life on land vanished. Pangea was a desert, surrounded by warm seas. A desert, desolate, in the wake of cataclysm. Though some life survived, subsisted, and changed and grew, life is always adapting to the circumstances that they're in, changing to the conditions that they change. The reptiles, they dominated, they loved this time. Scales and feathers, the dinosaurs. The dinosaurs dominated. The birds and mammals also appeared, but the dinosaurs dominated. Our Earth, Gaia, is spinning around the sun. And from afar, there's another asteroid traveling. We don't know how long, we don't know where they came from. Perhaps they were traveling for eons on a collision course. This asteroid, some 10 to 15 kilometers wide, this asteroid got closer and closer and closer and closer and closer and closer. And combined, smashed into the planet. On the Yucatan Peninsula, cataclysm. Our planet, it ended dark. Dust surrounded our planet for 1 year. No sun. Life died. 75% of life died in dust. Darkness for a year. Can you imagine? We wouldn't make it. The 5th mass extinction. As that settles, the dust settles. That one's close. 66 million years ago. We can still feel it. The dinosaurs. They died. They didn't make it. Their predecessors or their descendants, their ascendants, the birds, they survived. And the mammals, particularly the little tree mice, were all of our ancestors too. Common ancestor of all mammals, little sap-sucking tree mouse. Fortunately, that's another story. Fortunately, they survived, adaptable generalists. And the age of reptiles ended in that dust, and the mammals began to proliferate. Horses and whales and monkeys and antelope use their hands to manipulate the environment. The hominids, the Homo species, our ancient ancestors appeared somewhere in Africa, living and dying, just like all of life, living whole, rich lives like each of us. But not just because they were hominids. All life lives a full, rich life. Did you ever follow an insect for a day? They have crazy days. Crazy. They live whole lives every day. They live whole, complex lives. So did these hominids, living and dying and trying new things. Some 500,000 years ago, our ancient ancestors were wearing clothes. They were working with fire. They had axes and tools, likely song and story. Because fire, for so long, we couldn't make it. We had to find it. And when you find fire, you have to keep it for days and weeks and months and years and generations. We kept fire all together. And fire perhaps taught us how to sit in a circle, how to share food. Fire perhaps taught us how to tell stories and songs, because what do you do when you sit around fire for long enough? You share stories and songs and food. But can you imagine doing that your whole life, day and night? Day and night for eons. So like all life, we were changing and being changed by our environment. And some 200,000 years ago, the Homo sapiens, our species, appeared. And we are different. Not separate, but definitely different. I mean, look around. We're pretty weird. Really. But we're not separate. Our bones are like stone, our rivers are blood. Our microbiomes, our insides, our outsides on our skin are like ecosystems diverse. We are expressions of Gaia. We are expressions of the earth. And the earth is an extension of us. Just like all of life, this is Gaia. So what makes us different? We have an amazing ability to communicate clearly. And an amazing ability to collaborate clearly. Though that's likely because we're born so helpless. So helpless. Our gestation period is very long, but not the longest, but our maturation period is so long. 7 years, 13 years, 17 years, 27 years sometimes. It takes us a long time to figure out how to be okay, how to hold it together. Some cultures call our species the undone, the not quite finished. This, perhaps, is our greatest superpower, that we're born so helpless. We need each other. We need each other. And we have to learn our whole life the undone. And we have great power through that collaboration, communication, our opposable thumbs, our tool use. We can change our world. We've changed our world, not just in the last 500 years, but since we've been around, we've been changing our environment like all of life. And we shape our world with story. What we believe the world to be is the world that we make. The stories we carry about how things are make things to be, because we change the world with our thumbs, with our communication and collaboration. We shape the world with story. The earth is alive. You can feel that. This great story of becoming. We're not at the center. We're not at the center. We're on the edge of this story. We're on the edge. Right now, that story continues. With our breath. Where does that breath go? Out the windows, into the grass, turned into sugar, traded with fungi, down into the soil, where they're hunting for little nematodes with nooses, and they catch one and release that carbon back into the atmosphere, with spores as well as the trees, exhalation, our breath travels up. The spores, they condense clouds, making rain. As water condenses, it releases heat and rises up into the sky. The wind brings the clouds up into the mountains where it rains. That water and carbon combine again, making bubbles, carbonic acid. Thanks to lichen and mosses and plants in the mountains, the rocks weather. You see that smoothness on the rocks? That's the calcium and silica being broken. And they flow down in creeks and streams with our breath, that carbon and water. That's absorbed by algae, the coccolithophores, who make their bodies out of chalk. Calcium and carbon, silica for the diatoms. They make these beautiful geometric bodies. Many of these are eaten by smaller fish, the schooling ones, who are eaten by larger fish, who are eaten by even bigger ones. Our breath is in there. Eaten by the whales who go on huge migrations. The whales travel with our breath in their bodies down to the Arctic, up to the Antarctic. There, they're following these huge ocean currents, the global ocean conveyor belts, which start atolls. This mixing of cold, fresh water melting from the ice with the warm, salt water full of nutrients. When the ice water melts, there can be a thermohaline, a separation, a horizon of this warm sea water that's rich in nutrients, and this cold, fresh water full of oxygen. And when the whales, they get there, these seas are so rich, they are so excited that they play and they reach, they jump into the air and they smash the water. They mix the water at the poles. Mixing that water, it jumpstarts the ocean conveyor belts. The whales' play makes the oceans flow. And they follow that water, the currents they created with their play, back up to the equators and further. And along the way, they do as all animals do, they poo. And whale poo is different. It floats. And that floating poo is key nutrients for the algae, the coccolithophores and diatoms, which form the basis of their food chain. Those coccolithophores, when they die, they sink. Most are eaten, though some sink deeper and deeper and deeper. Down to the bottom of the sea. Their bodies pile up for eons. And their skeletons, made of the mountains, turn to stone again. Sedimentary rock. The movement of the tectonic plates. Subduction, they sink. Deeper into the earth. Where it's hot, they melt. Magma. It could be 10 to 100 million years, remember. Our breath is in there too. Sinking down, subduction, molten magma, lava, eruption, the volcano, carbon released to the atmosphere. Warming our planet, fertilizing the forests. Water and carbon combine the bubbles, carbonic acid, calcium, and silicon flow down to the seas. Cycles and cycles and cycles and cycles. Some of those coccolithophores, we have to talk about them again. Some of them, when they starve, they release a gas. Dimethyl sulfide, which floats up into the air and, like the spores, condenses clouds, making rain. And some of those coccolithophores who are lucky to be at the surface, they catch a ride with the upwelling currents that the clouds create, and they fly. The clouds, that's not just water. Those are microbial ships. They're full of diversity, full of life, and created by life. The clouds are blown by the wind from the whales inland, where the trees, the forests, all around us are breathing like us. They're exhalations and inhalations. They're breathing with us. Every breath we take, it's an active participation in the making of our planet. Every breath we take has gone on these millions of year journeys. What are we infusing in our breath? What are we infusing in our breath? What are we sending on those millions of year cycles? Gratitude and wonder and awe and praise. Wonder.
Thank you all so much. Thank you so much. We just barely got that together. Thank you. Just barely. Right on the dot? Yeah, right on. Thank you so much. That was, these are like I said, these are stories. This is a true story. These are all true stories.
These are what our scientists know so far.
This is what we know so far, based on our science, ecology, cosmology, geology, all together. This is Gaia, our living planet. This is our origin story too, our cosmogenesis, how all this came to be, where we come from, and two, who we are. Thank you so much for being here. Thank you so much for listening. I want to give such deep praise. My teacher, Stephan, who passed a month ago. I learned these stories from Stephan Harding. He wrote the book Animate Earth. I have a copy of it every year. You can take a picture, check it out. And it's his memorial today. It's his memorial today. And he would love this so much. He'd be up here with the Quattro, just tearing it up as well alongside. So total praise, respect, admiration.
His legacy lives on through you.
Yes, yeah. Stephan Harding and his teachers, Lynn Margulis and James Lovelock. So lucky to be here. Thank you so much.
Thank you.
You're welcome. Yeah. And I'll just hang out here for a little while. You can come say hi and share hugs and stuff. And I'm just starting to do this. Like, this is so fresh. This is like the first one, basically.